Good afternoon, everyone. Today is the first lecture for the series of IAS Nobel Prize Popular Science Lectures. Today's speaker is from Professor Kensing Wang from physics. He actually got his PhD back in 1987 in Oxford University, and he joined physics department at HKUST as a founding member in 1991. Okay. Now he's a full professor in physics department, and his main research interest is very close to laser. Okay, so including ultrafast lasers, nonlinear optics, time-resolved spectroscopy, semiconductor and polymer physics. So he's most suited for today's talk and introduce to us about lasers from manipulating a single molecule to creating the power of sound. Okay, let's welcome Professor Kensing Wang.
So good afternoon. So before I start, I must thank you, IAS, to let me present, well, at least tell you a bit more about this year's Nobel Prize in Physics, to explain a bit more physics behind it, why it's so important and so on. And so this is the title, Laser from Manipulating a Single Molecule to Creating Power of the Sun. Well, this is outline, so I don't have to go through. But before I go to actual Nobel Prize stuff, I just say a few words about laser, because that's the first word in my title. So, I mean, this is a picture from this illustration from the book by, famous book by H.G. Wells on the War of the Worlds, okay, in 1898. And people have science fiction writers already have the vision of this using intense laser, intense beam of light as a weapon, as a tool, whatever. Okay, so this was 19 years before Einstein, proposed this stimulated emission of photons. That is, of course, the basis for lasers. So, people had think about it, on this direction long time ago. And since then, of course, I mean, you see many movies, Star Wars, or Star Trek, whatever. The lasers used as a weapon or tools. It's a lot. I mean, substantially. Okay. So it's very important. And but sometimes, actually, we take it for granted. A lot of our daily life, actually, involve laser. You may not realize. Okay. For example, I mean, DVDs using laser to read. Okay. Supermarket scanner. Okay. You see a scanner. But very importantly, for example, all this network here in the university or in Hong Kong, most places, using optical fiber, okay, for internet, for telephone, not your mobile phone. Of course, mobile phone is using microwave. But that in the optical fiber, of course, you're using laser, okay, to transmit the data, the information. And for us, for do research, that's, again, is very important, one of the most important tools nowadays. I mean, not only in physics, in chemistry, in life science, in engineering, it's very important as a tool. So, in fact, of course, it's been recognized. Nobel Prize this year is related to laser, but last few decades, several Nobel Prizes are related to laser. I mean, most recent example, well, this one last year, the gravitational wave. I mean, that's for detection gravitational wave. But the tool they use, okay, is by interference of laser to detect this gravitational wave. So they're using lasers. Okay, so it's become very ambiguous in our life. So okay, now go to the main theme. Okay, so as you see a picture here, this is Nobel Prize in Physics. The winners are half of the prize is to Alfred Ashkin for his work on optical tweezer and application of the biological system. The second half is to to Gerard Moreau and Donald Strickland for their work on method of generating high-intensity, ultra-short laser pulses. Okay. I just say a few words about Donald Strickland. In fact, you look at the Nobel Prize winner, she's only a third woman winner in physics. Third. Last one was, I think, Maria Goldwyn-Mayer, okay, in 1963, 55 years ago. The first one, of course, is Marie Curie in early, I think, 1903 something. I forgot exactly the date. So it was 55 years ago, last time. But hopefully, because next women's Nobel Prize winner in physics, it should be sooner. I guess it must be, because nowadays the gender diversity in physics department are a bit better than, let's say, a few decades ago. Okay. So let's start with optical tweezer, the work by Alfred Ashkin. Okay. So basically, his invention, he basically showed that you can using laser, okay, to grab hold of particles, okay, not only particles, in fact, atoms and molecules, and use that, okay, to do experiments, different type of experiments, okay, and so on. So, but using laser to grab hold of things, okay, again, it's not, it's demonstrated experimentally by Ashkin, but again, science writers have been, using this concept for a long time. And again, in this movie and so on, you got tractor beam, the grab thing and moving around, or grab the spaceship, whatever. Okay, it's many decades. Okay, we're talking about, and in fact, we know, okay, for a long time, okay, light could exert a force on an object, isn't it? Okay. No. Well, first of all, I mean, light, although photon, no mass, but it has a momentum. Okay, so it has momentum. When you hit something, of course, conservation momentum. You say then you could move an object. You exert a force on it. In fact, it's the first Kepler recognized this. Okay, but look at these comets. You can look at the tails of comet when they move through the sky. But always, the tails always get away from the sun. Okay, see in this picture. Okay, then his explanation is a radiation pressure. Okay, the radiation, the sun, the photon is sun. Okay, to push the tail basically from the force and momentum, push the tail back away from it. Okay, so indeed it's the case. Okay, so light will exert a force on an object it hits. So, this is a list of some of the pioneer work from Ashkin. From basically, he's in this business for a long time. He's now, I think, 95, 96 years old. So he was in Bell Lab, and then he's been doing research since the 60s, 70s. So very first paper on related object, 1970, on basically demonstrate optical force by laser could displace and small dielectric particle. This is displacement, not the grabbing, not the tweezer yet, but later on 80s and 70s, and when he able to show it, and then also he another one you see the work together with Stephen Chu, and on using the optical tweezer whole atom and laser cooling, and he was a co-author in this paper. And then, of course, at the end, this laser cooling atom was awarded Nobel Prize in 1997, okay, to Stephen Chu and two others. Okay, later on, you will show. Okay. So anyway, so the photon and momentum when it hit an object, it exert a certain force. Okay. But of course, this force is very small because that of course depends on your intensity, your beam also. So at least normally you go forward. Okay, you go forward, but if this object is large, then of course you basically will not move. But it's small enough, your beam is intense enough. In principle, it can move. Okay, and but for laser beam, okay, it's not uniform. Okay, not a uniform intensity. Normally it's a Gaussian type. Okay, so that in the center is a bit more, is much stronger than as go away from it. Okay, so therefore, this what they call a gradient force. Okay, gradient force. From the side from the center to the edge. Okay? So, I mean this diagram. So what will happen? Okay. So if suppose you got a B, okay, a small B, stand in the middle of B, then of course radiation pressure will push forward. Okay, if you're not strong enough and so on. But if it displaces away from it, okay, displaces away from it. Let's say in this picture here, a bit below the central axis. Okay, then the strong beam in the center will be reflected downward. Just simple optics. Okay, simple optics. Now, again, I mean, from conservation momentum and so on, you can see there must be a reaction for the piece go back up. Okay, I mean, it may not easy to see, but you think instead of way uptake, think as a photon. When the light collide with the beam, the glass beam, for example, okay, then the photon go downward. Okay, then the particle must go upward, isn't it? I mean, if you play snooker or billy ball, I mean, just collision. In that, you could think in this way. But from this diagram, from conservation momentum, you can see is a force and push it back into center by this gradient force. This gradient force. Okay. So now, of course, this. Well, anyway, so for vertical one, then of course, I mean, if you this gradient force you hold it in the place, and then also you got this vertical pressure, vertical fold up, so you could grab something against gravity in the mid-air. Of course, you can do that quite easy. But in practice, of course, the laser beam itself, you're not focusing it. It's not strong enough. So in order to see this effect, like optical trees and so, you need to really focus it very tightly. Okay, so normally you're using let's say optical microscope, using objective. Okay, so that you really focus the beam in the small spot. Then this gradient force, okay, the gradient force to basically push the beam back. Like this example, this drawing here. Again, this is from one action paper in 1986. Okay, and now when this is center of focus. Okay, without the beam. Okay, with the beam, it will reflect in this way. Then it's a net force push this is a glass beam, for example, back to the center in the focus. Same thing up the top, so that basically, if your beam's intensity is strong enough, the gradient force is sufficient. You move the beam, if they're away, not too far away from the center or the focus, you grab it and push it back in the center, hold it in this, become stable. So you basically grab a glass beam, for example. So of course, with this, it's very important. Okay, this is for glass beam. This is using classical optics, but of course, in fact, you could apply the molecule or atoms using dipole consideration. Then it's the same thing will happen. So this can not only grab physical objects like bees and so on, but you could grab atoms, grab molecules. Then you could study basically individual molecules and atoms based on that. Okay, using this technique, this technique. Then of course, Stephen Chu, Claude Cohen, Tanaji, and William Phillips, they're using this to hold atom and then using laser to cool it down to basically here there's a mini Kelvin, but nowadays people could cool it down to nanokelvins. Okay, like work using combination laser cooling, other types of cooling to very low temperature, and this was awarded a Nobel Prize in 1997. Okay. So this Nobel Prize 97 now is 2018, 20 years, 21 years. So, but HKUST is a precursor for this basic Nobel Prize. So with this, the whole individual atom molecules, then people could able to do a lot of experiments relate to some physical process and property of individual molecules. Before, it's very difficult. I mean, very difficult to look at individual molecules separately, but now with HKUST, then you could do it. Okay, so basically, one important work is on in molecular level metrologies. This example here, they put a DNA or something, attached to a glass bead, hold a glass bead, and then you could unfold or fold the DNA and so on, so that look at this folding and unfolding a single molecule RNA and so on. And then you could basically perform single molecule force and motion measurement. This is very small. I mean, they talk about nano-Newton force. And one example here is, in this example, they look at this protein. Again, I'm not expert in chemistry, so I just about this myself, so I can learn myself from here. So this casein, this is a protein, but it's a protein very important for transports in the cell. Okay, it's a cargo. Okay, it's like truck. Okay, transport large molecules, because small molecules diffuse through the cell from one point to another, but for large molecules, it cannot diffuse, and they're using this protein to transport from point in the cell from different places. So that's therefore some of the property very important. For example, how fast they move, what's the force they exert on the object, and so on. It's important to know. And then again, they're using this HKUST, but basically again you attach this to a glass bead, okay, and then you use HKUST to hold the glass bead, and then when this ring moves, of course you will pull the bead, and then you can measure the force, measure the distance, okay, it moves, or what's the force they have to move the object. And in fact, in the measurement, they can clearly see each step they move is about about 8 nanometers each step. Okay, basically, I call each step we move about 8 nanometers, and the force involved something like in few pico-Newton region. Okay, this is another. Okay, this one I don't know how that is. I don't know how to work on this one. This one on here. On here. Okay, doesn't work. On here, before I try it, okay, it works here. Okay. So this is a movie of they basically they using that to do a real-time imaging, okay, and also of imaging and also movement of object. Okay. Here they're using optical tracer whole blood cell. This is imaging of blood vessel or of mouse under how many 40 micron beneath the surface. Then you can see. I mean, for example, here they want to study the blood clot. Okay, how the blood up in this for stroke and so on is important. Isn't it? So you can see they can hold it, and then with the clot, then they can move it and then unclot it and so on. So this is that kind of application, at least in biology and life science, is very, very important. So So basically, this is what I said. Optical trapping has gives unique insight into mechanism, mechanic, and fundamental molecular process. Okay, and this basically this optical chooser open a new world for people, especially working on life science. Okay, but not only that, but people in other areas, in physics. I mean, for example, Nobel Prize in 1997, optical laser cooling. I mean, that's based on that. Okay. So, in fact, some of my colleagues in Department of Physics, actually doing some work related to this area. So I'll give you a couple examples. I mean, not in physics, not in life science. Okay. So the example I give so far, okay, single optical trap. Okay. Using a laser, you focus it, and you got one trap. But in principle, you don't have to make multiple traps. Okay? You could, using, for example, laser interference technique or other technique to make 2D, 3D optical lattice. Okay? And then you could also control this. I mean, all this, each lattice, of course, each point, okay, is a trap. Okay, and you could using that to trap atoms or trap other molecule, whatever you want. Okay, and then you could also control the spacing, okay, and the structure optical lattice by basically using different interference by angle intersections, the wavelength the laser you're using, and then number of laser beam used. So then you could produce, for example, like real crystal. FCC structure, BCC structure, and different type of lattice structure. Then you look at the interaction of the atom molecules in this type of different structure or different spacing. What we do, what my colleague Joe do. In this case, he made multiple optical lattice, 2D or 3D, depend what he want to do, and then they check atom on each trap, and they cool it using laser. We call laser cooling and other cooling, cool it down to millikelvin temperature. Then of course very low temperature. Then he could. This is not a platform to do all this type of quantum simulation or different type of quantum optic or quantum atom experiment. For example, in here, I mean, you can see quite. I mean, for example, you check an atom with the control spacing, as mentioned, by looking by different laser wavelength or angle or angle interactions. So give you the lattice spacing. Then you could look at the short range ordering or interaction between the atoms or formation for molecules. I mean, molecule, of course, this from atom. When you could code the positive attraction, they may form molecules. Okay. So you could look at the quantum chemistry or universal behavior of this cold atom at low temperature, okay, at different distance. And I think it's one recent work published just recently at Science Advance that is looking at topological insulator. I think relate to this. So not only in life science, in physics, okay, it's a lot of application using this optical laser choosers. This is now from my colleague CT. I think he's here. Okay, so he's also been working. One area is on this optical force. Now, science fiction, okay. Star Wars you see all the time. Laser beam and grab another spaceship and then you pull or hold it or pull toward you or something. Science fiction is possible, okay. But textbook or normal, intuitive or simple logic, you think it's not possible because we just mentioned, photon momentum. Okay, so it's going forward. Your beam going forward. So when you hit an object, you only push forward. How do you grab it? Grab it and take it toward you. Okay. Now, in the optical tracer, optical tracer, you grab and you can move forward and backward. Yeah, you can do that, move backward. But that's not, it's the different case. You move backward by moving let's say the focal point back, and then up, you grab the object, you're coming back. Okay? But in this case, when you found optical pulling force, is really a laser beam, let's say, is sufficiently strong. Then an object, you hit it, then the force will pull it back, not without moving the focus back. Okay? So well, that's a statement from Alfred Clark. The only way to discover the limit of possible is eventually beyond impossible. Of course, CT, he believed in that, which, you could try the impossible. Of course, it's not impossible. I mean, otherwise I won't show you. It's possible. Okay, it's possible to create a pulling force, from light. You could pull an object back. But, of course, in this case, it is a special situation, okay, only certain situation. Okay, so the beam you need is what they call a special beam, okay, special beam, okay, a special beam, okay. So, and not only that, okay, I think this, okay, the special, probably a special beam is, okay, the pen wave, okay, the K vector is just around on a cone. Basically, probably the special beam is in the center, okay, the K vector in the z direction is less, okay, than those around it, okay. Unlike Gaussian beam, for example, which is other way around. Then not only that, when you special beam hit object, and this object has to be a bit special, so that when you scatter the photon or light, most scatter light in the z direction, K4 direction. Okay, so that when you look at this, I think it's something more G. I'm not sure G there, but it is in the outward, in the z direction. Okay, it's less the outward than the coming in, like conservation momentum. Of course, the particle has moved backward. Okay, moved backward. Then light come in, then particle with condition correct, it can pull back. Okay, so I mean, this of course is this work again published in 2011. It's a theoretical work, but only 1 year later, okay, 2012, it's already free paper. 12, 13, so 1 and 2 years, they already free paper published. Proof that, experimentally proof. This is indeed the case. This is indeed the case. So, it's not impossible. It's possible. So when someone told you something not possible, don't always believe it, okay? You need to go try yourself, see whether it's impossible or not. So, okay, it's good, half hour. So I'll go to the next topic, basically next half of the Nobel Prize on amplification of very short pulse and very high power laser pulse. Okay. So the word that people using, what they call, the technique they're using, or what they invent by Ashkin and Strickland is called chirp pulse amplification. Chirp pulse amplification. So again, this is the some important landmark. But this concept, chirp pulse amplification, is published in this paper in 1985. Okay, or compression of amplified chirp optical pulses. This was I think she was a PhD student of Murray at that time, and at that time they are at Rochester. Okay, so again, so before I go to that, basically, for generation short pulses, of course, it's very important, especially when you look at something you want to look basically faster and faster event. You need shorter and shorter laser pulses. Okay. Of course, you want high intensity so that you could access to some phenomenon. You need high energy. Okay, nonlinear regime, for example. Okay. So, I mean, when you look at something like millisecond or microsecond scale, of course, using normal camera, you can do it. Okay, but even camera, you are shutter to control the speed. Okay, and then but for nanosecond or even picosecond, this is nanosecond. You could using oscilloscope. Okay, it's electronic. You record these events at that kind of speed. For picosecond, there's some other electronic equipment called strict camera, for example. You could go into picosecond. Okay, picosecond, 10 or 12. But beyond that, okay, sub-picosecond, basically is no electronic instrument really able to go that fast to record it. Okay, so the only way at the moment, basically, to look at sub-picosecond events and so on, you need using optical technique, essentially optical technique. Okay, so you're using basically femtosecond pulses, or later on, so it's called attosecond pulse, 10 to 8, femtosecond 10 to minus 15, attosecond 10 to minus 18. Short laser pulses. Look at, for example, you want to look at the electronic process, okay? Electronic process in this example, photosynthesis, but many electronic process, okay, in semiconductors or in molecular, in molecules or chemical reactions. It's talk about picosecond to femtosecond time scale. Then you need to have a laser at that kind of time scale to probe these interactions. When you go to electron motion atoms, okay, or interaction of nucleus, this very strong force, and then the time scale is much faster. So you need to go to some kind of attosecond time scale to do it. Okay? So this is a famous table showing the evolution of laser intensity with time. Okay, so so you can see. So in 60 to 70, okay, only 1960 we invent laser. I mean experimentally. Okay, so because it progressed very quickly, your Q switch and so on, you got nanosecond pulse, and then invention mode locking in late 60s. Mode locking is the way you get short pulses. Then you can increase the I mean, how you increase the intensity of power? Okay, of course, power equals energy of pulse, and over time, the time is a pulse width. Okay, so therefore, you want to increase the power, you either amplify your pulse. Okay, so that's a big contribution from Strickland and Moreau, and or maybe very short. Okay, so that the T becomes small, then power becomes large. Left-hand side on this diagram is this called intensity. Basically, you normally focus the laser in the spot, typically a few micron in diameter. Then that's the intensity you could reach. Okay, so at that time you could reach 10 to 12, 13 watts per centimeter quite easily. But then it reached a plateau. Okay, at this about 10 to 15. Okay. Or basically in the 80s, early 80s, okay, with mode locking, with amplification and so on. Mode locking, at the most you get even the best one. At that time, you could also make about 30, 40 femtosecond pulse width. Okay, but problem is amplification. Short pulse, you amplify a pulse. Of course, intensity increase, the power increase. Okay, then you amplify further in your amplified medium or some other medium in your laser cavity. You will damage the medium. Okay, you will damage it because the peak power is very high, and then you got pack a lot of energy in a very short time. So you cause damage. Okay, so before I do that, so of course this chirp pulse amplification invented in 85, 86. Then you will overcome this problem. Then you could amplify it, very high intensity. Then you could go to intensity, something like now 10 to 20 or more. Now, of course, they plan to go even higher. Again, we'll talk about this later. So actually, chirp pulse amplification, the two, one stone to kill two birds. You not only amplify to high intensity, but it also find a way to achieve even shorter laser pulses. Because as I mentioned, for short pulse using what we call mode locking, basically you are using some special technique. You lock all the laser mode together so they synchronize. In this case, instead of randomly occur, then you're able to produce a very short pulse. In 80s, basically reach a plateau. Is a plateau not only the power but also the laser pulse width. Laser pulse width at that time only down to a few, at that time probably 10, 20 femtoseconds. What's the limit for shorter pulse? The limit is basically uncertainty principle. So uncertainty principle, you know, I mean, from high school or university, you learn is if delta P, delta X greater than H bar over 2. But that's in momentum and space, and uncertainty, momentum, uncertainty in space. But of course, you could change it in delta E, delta T, delta E, uncertainty energy, delta T, uncertainty in time. So for laser, of course, it is pulse width, delta T, and delta E is the energy, the uncertainty energy, basically the bandwidth. You bandwidth your laser. So for laser, the shortest pulse laser you produce, using what they call titanium sulfur laser. It peaks about 800. And then if we bought spectral bandwidth, we could produce a bandwidth something like 600 to about 1 micron. So it's huge, several hundred nanometer. Of course, you want to mode lock into a few femtosecond. The record now is about 5.5 femtosecond. Basically, you need to mode lock all this bandwidth in this sulfur laser to get this one. But that's it. You cannot go any further because there's no more bandwidth for you to pay. So, and there's no other laser sources sufficient large bandwidth to go to, say sub-femtosecond. It's not possible. So that's a limitation on that already. But the CP chirp pulse amplification able to find a way to overcome this problem to produce what we call attosecond pulses. So I mentioned if you increase the power, then basically you will damage, you will damage the GaN medium, essentially GaN medium. Basically, GaN medium is just some glass crystal, for example. It says have a certain damage threshold. So once your power above the threshold, we will damage. And once it's damaged, you cannot use. So that's the reason it's a limitation before this chirp pulse amplification. Another thing is a phenomenon called self-focusing. Self-focusing. Again, it's just because as you go to high intensities, then the nonlinear effect will become important. For example, for laser, we mentioned it's a Gaussian beam. TEM COCO mode is a Gaussian beam. That means the center, a high intensity compared to edge. Most material, will the index refractive index not constant. It's a nonlinear. High intensity is a intensity dependent. So normally, actually, very often it is high intensity. It's positive, so that it is an increase. So in the center of the beam, when the light propagates in the gas medium, center the beam intensity higher compared edge, so you get this profile, okay, as a function distance. Then, well, you know how optical fiber works, isn't it? Okay, optical fiber work basically, centers high index, edge is total internal refraction, you confine. But here is similar, okay, similar phenomenon. Your center is higher than edge. It acts like a lens, the index, so that you will converge the beam. Although the gas medium is uniform, okay, it's not a lens which is like curved, but because your index profile, high intensity, then the beam is self-focus, converge. That's how you damage normally, okay? Not because simply increase the power. Increase the power, and nonlinear effect come in, it's self-focus, and then you burn your gas medium. So that's previous limitation on that, okay? So, of course, idea of Morel and Strickland is, okay, what about the individual wavelength, okay, for short pulse, okay? Then there's many femtosecond, your bandwidth very large. That means you many frequency components, okay? So what about you separate different frequency components? So you basically broaden your pulse from femtosecond into nanosecond or picosecond pulse. So you broaden it, then amplify it. After amplification, then you compress it again. Okay, so that is how it works. Then of course you overcome all this self-focusing, the damage, okay, in your gas medium. So this, as I mentioned, this is the paper published in '85 in optic communication. Again, thing for students. Everybody try to publish in Nature and Science nowadays, I guess, but this optical communication is at that time, even if 85, not the top journal, okay, not the top journal, okay, but this is Nobel Prize work, okay. So don't be discouraged if you only able to publish in maybe APL nowadays, no problem. It can be Nobel Prize stuff, okay. Of course, you could publish in Nature and Science. It's great, but if not, some decent journal is still good. Anyway, so you can see a diagram. The diagram, okay? So you got at that time, 85, in this, they're using a YAG laser, a Moloch YAG laser. The output is only a picosecond, the pulse. Okay? Test alpha, you go femtosecond, even 85, okay? Okay, 85 is not just started, not quite test alpha laser, not very fully developed. Okay, so people short pulse femtosecond or picosecond laser using YAG or using dye lasers. So the pulse width is about 2 picoseconds. It's still quite short. You cannot go any shorter because YAG laser is neodymium, is iron. Emission is very short, bandwidth very small, so you cannot go to very short pulses. But it's still 2 picoseconds short. Then what they do, they put this into fiber, 1.4 kilometer fiber. So fiber, of course, is dispersed, glass, and it's a function of wavelength. Okay, so that as it propagates through the fiber long enough, then it broadens. Okay, it broadens the pulse. So bottom, basically, you use different frequency component. Instead of move together, it's just out of sync. Okay, so that your pulse, your different wavelength in frequency or frequency wavelength in the pulse, moving at different space and time. Okay, so then when they broaden, they amplify. After many runs, enough power, they switch it out, and then using a pair grating to compress it back into the 2 picoseconds, back to picoseconds original. So that is first demonstration. Of course, it works, and then people realize this is very important, and then nowadays, basically all these high power lasers, okay, the femtosecond one, okay, not the nanosecond one, the femtosecond high power laser, or using this what they call chirp pulse amplification. So basically, this diagram expand a bit more detail on it. So basically, you got a femtosecond pulse, for example, come in. In here, nowadays, instead using fiber to stretch a pulse using a pair grating again, because it's simple, a grating fiber, you need to focus it and very easy misaligned and so on. So now they don't using fiber. Okay, you're just using a pair. Again, grating is very good. Okay, of course you lose some light. I mean, 18 is still about 80 or 90% refraction. You lose about 10 or 20%, depending on how good your grating. And then you basically disperse it. Okay, disperse it, and then both in space and in time. So different initially when they're what they call transformed limited pulse width. All the different frequency or different color of the component in the laser pulse basically move together so that you get short pulse. So this one basically, right, you separate different component, okay, in space and in time in this case, okay. Then your pulse from, let's say, femtosecond into tens or 100 picoseconds, okay, and then you amplify. You amplify the very high power because now the pulse width is much longer. Then this self-focusing effect is much smaller. Then you could amplify very high power without really damaging the amplified medium. So after amplification, now intensity much higher, but pulse still very broad. Okay, then of course you could basically this is reverse this one. Okay, using a pair grating again to compress it into the original pulse width, but now the intensity is much higher. So the concept is very simple, but it's a very powerful technique. Okay, I mean, good idea don't have to be complex. Okay, simple idea as long as work is important. I mean, now as I say, every femtosecond system essentially, okay, high power femtosecond system are using this technique. So as you see, if you this is 85, and then with that, it pick off the intensity able to produce it go very rapidly. Okay, very rapidly. Okay, with high intensity laser, of course, you enable you to do a lot of relativistic optics. Okay, or nonlinear quantum inertial dynamics. Basically, you could using very high power laser to do particle physics essentially, for example. Okay. Well, this gives you a little bit idea how for example, now you can amplify to 100 joules with 100 femtosecond. Okay, so you calculate. I mean, you talk about terawatts, petawatts. Okay, petawatt power. Okay, 100 joule divided by 100 femtosecond. Okay, femtosecond 10 to the minus 15. Okay, so this is 1 times 10 to 15 watt. So this is petawatt. Okay, huge power. Okay, huge power. You look at what's the power consumption of the for the electricity consumption in the world. It's about 11 terawatt average. Okay, so this is about 100 times. Okay, from this 100 joule, 100 femtosecond laser. Of course, this is average. This one only lasts 100 femtosecond. But you can see how much power you pack all this power into very short time. Okay, so you could, as I mentioned, you can using that to do nonlinear optics. So let me speed up a bit. I'm a bit running out of time. So then, of course, using high power, short pulse, you could do one big application is to do time result measurements. Okay, so this picture here, is a fast camera. You look at how the bullet hit a apple. You could capture it. Okay, but with something even faster. Okay, this is something like milliseconds. camera cannot do that, not fast enough, something like, let's say, nanosecond or picosecond. So you need, shorter pulses to capture all these fast events. Okay, so I give you a few examples. Okay, type of experiment people can do, time resolve experiment, to look at different fast phenomena. I mean, of course, one good example is the work by Sirab he got Nobel Prize in 1999 on what they call femtochemistry. Basically, he looked at chemical reactions, okay, in the femtosecond time scale. Okay. Basically, in this case, you're using femtosecond laser or shorter. The example here is look at this iodine cyanide, okay, reaction. When you excite it, so it's an intermediate state, and then in the initial here, and then they will, of course, very quickly relax down in this excited potential, and then at the end, it will ionize, separate. Okay, so you could using the optical technique, we call pump and probe technique, to look at these intermediate states. Okay, all these are within few hundred femtosecond time scale. So in order to see this kind of fast event, your laser pulse has to be in this case sub 100 femtosecond in order to see this fast event. Okay. This is a bit of what I'm doing myself, and one only slide, okay, for my own work. So one area I do is doing how does charge carrier generated and transported in the solar cell, in solar cells. Okay, so this organic solar cell, it's a bit complex. Because organic materials, when you form as exciton, the exciton is a neutral charge. It's no good for solar cell. Solar cell, you need electron and hole separate. So they separate at this junction. Okay, at the junction. Okay, where they're using what they call this Doppler acceptor. You're mixing two type of organic material to get one Doppler acceptor. So they separate only at the junction. Initially, they form what they call charge transfer state. Okay, so the positive charge on one side, negative on one side, but it's still bound. Only later on they will separate. But you can look at these intermediate steps by again using pump probe. I mean, from pump probe you see the band edge shift with time. Okay, because when you have charge at the interface, you produce electric field. Okay, electric field. Then of course you from other experiment in CW DC measurement, you put electric field across let's say this material or most semiconductor, you produce what they call star effect. So this is called the optical star effect. Then you cause a shift in the band edge, and then you can see this very clearly shift with time. So that you can see how far the charge able to migrate from the bulk into the interface and then separate. So you can trace the transport of this of the charge and excitons. Okay. And of course, other motivation is for applications for industrial use. Okay. So one very important area is for cutting or surface finishing, okay, of material. Whole point is for femtosecond laser, it's you pack very high power in very short time. When using nanosecond laser, okay, to cut things or drill holes in the metal and so on, you're basically using heating. You melt the material and then break it, okay, or make hole into. With melting, basically, you produce a lot of debris outside. So when you cut and so on, it's very, very rough. But with femtosecond laser, basically, you don't go through melting. You go through like chemistry, sublimation. You basically completely remove the atom, okay, from solid into vapor, okay, so that you don't have the melting process, you don't have a heating effect, okay. Then your cut is very keen. The cut is very keen. And then, of course, you do very precision cutting and patterning in this. And then, of course, you could do other application in medical use. You do imaging. You could, from nowadays, you're using femtosecond laser produce X-rays, coherent X-rays, short pulse. okay, femtosecond. Okay, then you could do time resolved X-ray or using phase contrast X-ray. Phase contrast, you get much clearer imaging of the objects, and of course another big application for laser. Okay, by basically, some of you maybe done this here already, but you could, the ring glass is not so convenient. You could using laser to re-profile your the retina, okay, cornea, okay, so that you compensate whether short side or long side, okay, so that femtosecond laser, because no heating, okay, no damaging, then you could very precise control the cutting and so on. Then you can using that. Okay, in fact, a lot of this, or nowadays, all the laser they do using femtosecond lasers to do. Okay, so. As I mentioned, another big breakthrough is using this chirp pulse amplification, this generation of attoseconds. Okay, attoseconds. The way, basically, that was only later on, initially people didn't realize you can do that, but only later on, then when you experiment, people realize. Very simple, you will focus a high power femtosecond pulse in the jet of gas or a gas in a waveguide, you will produce high harmonic generations. Okay, high harmonic, 30, 40 harmonic. Okay, that means in a deep UV or near X-ray, soft X-ray region. Okay, and then these are coherent. Okay, so I say the bandwidth is not enough. Deep in that, when you go in deep UV, then you shorter wavelength, and all these different harmonic also they are coherent. Then you're able to produce attosecond pulses. I mean the detail. I think I'm running out of time. I'm not going to go through it, but it's basically due to basically tunnel ionization and the acceleration by the E field, and then later on recapture, okay, by the atom, okay, and then because it's still in excited energy, and then when they come down at the bonding energy of the orbital or different orbitals, okay, and then give you different harmonics, okay. So basically the setup is quite simple, relatively simple, okay. You just focus on the jet of gas, but nowadays they normally put in some kind of cavity so that interaction length longer in the waveguide, the gas in the waveguide, and then the efficiency much higher. But this, for example, one example from this Eli Bin's recent output, they got this is start with the 14 femtosecond pulse. It's a touch alpha laser. So the peak wavelength about 800 nanometer. So you code, so it's about this wavelength. Then basically the harmonic generation you get into 30, 40 harmonic, okay, of this, okay. In your nanometer, now about from 800 nanometer into 30 or even 20 nanometer, okay. Then you could calculate the bandwidth available. Then this is. This pulse here is a femtosecond pulse. Again, they have measured. So basically, with this femtosecond pulse, okay, then we could investigate even faster phenomena. Okay. So ionization or collision electron from parent atom time resolved photoelectric effect. That's a recent publication using this attosecond pulses. You can do this kind of spectroscopy. Okay. Another example here. Here is work from a group in NTU, but also although this work was back in 2010, he was still in Stanford. Okay. Look at the oscillation, okay, of electron, the interference between, okay, the different energy states. Okay. So that you get the basic bitting effect. But this time scale you can see, okay, is a few femtosecond, okay, the period of speed. Okay, so that again you need attosecond resolution to see this kind of effect. Okay. So okay, of course, one very powerful incentive with high power laser for use it high power laser to inertial for nuclear fusion, laser fusion. Okay, the biggest laser in the world now, of course, is from at the U.S. in Livermore, you call National Ignition Facility. So this is size. I mean, this is only part of it. I mean, size of building. Okay, this I think almost 200 billion focus in a small, tiny target to create fusion. Now they get, of course, now quite big progress. They get actually more fusion energy output than what they put in. Okay, but it's still a long way from commercial process. But this laser, okay, we say is not, it's actually nanosecond laser. The amplification, they do not using chirp pulse amplification. But now some new system building up. Okay, other countries now, of course, are doing this. Okay, in China, the two facilities in China are, all these military facilities. I don't know what exactly the status, but they are using, they doing nuclear fusion, okay, laser fusion. Japan, they have facility, okay, and the Japan one, in fact, you can see they're picosecond. So picosecond pulse, you have to using chirp pulse amplification. Okay, so in fact, there's a, as mentioned more, using femtosecond pulse, you may be able to get faster, okay, fusion process. Okay, at the moment, not been done yet. And also, the theoretical prediction using proton boron 11, okay, fusion. But in this case, you're using a femtosecond pulse to excite. Nanosecond will not work. Then you get better yield. So some people, for example, in this facility, I guess they will probably will try to work on that. Okay. So laser fusion not only limit to this big national facility, you could do it on tabletop. At the moment now, you're just in a lab, you have sufficient intensity and short pulse. You focus in some target, in gas or in some solid target. You can produce the tabletop fusion reactor. Okay. Had been demonstrated since the first one, 1999. Again, Livermore lab. Latest work, you can people that publication on that is only this year. Okay. So, but this of course not really for energy production, but really is a neutron source. Okay, neutron source. Okay, you could produce neutron in the fusion. That means one way they find is fusion process in neutron, a certain characteristic wavelength energy. So as a neutron, a tabletop neutron source. Normally, you do a neutron experiment, you go to nuclear power station and nuclear reactors. But now, in principle, okay, with that, you could do in your lab. Not only that, this neutron is pulse. Well, this is not the energy, but this is from femtosecond pulse. So the neutron also pulse. Again, you could do time resolved measurements. Okay? Neutron experiments. Okay? So with this this amplification technique, now people are now able to produce very high energies, high power. Okay, so one major push, of course, is from Moreau. He basically convinced or made a proposal to the European Union to set up this what they call extreme light infrastructure. Okay, ELI. Okay, so we have 3 sites in Europe. One of them is already commissioned. So basically in all of them in former Eastern Europe countries. Okay, and there are different roles to play. So this one at Prague, Czechoslovakia, or Czech Republic. So it's high beam light facility. So this really to produce high energy particles using pulse laser, not from accelerator. next slide will show you using a laser to accelerate particles, okay, using plasmonic wave, okay. So that the target is 10 gigawatt EV, sorry. But ultimately, the diagram you see next, they won't go up to tera EV, okay. That's comparable to collider energy, okay. Then this one in Hungary is for attosecond pulse, okay, but very high power, talk about several hundred petawatt power, okay. So then using that will generate extreme UV and soft X-ray, but attoseconds, okay, a few attoseconds in pulse width. Then really this you could have extremely high intensity, then to probe essentially atomic physics or particle physics, do experiments. And this one is more for nuclear physics facilities, okay. So I'm running out of time. I want to finish off a couple more slides. Of course, China, not only in Europe, they have this. In China, they have coupled this extreme high intensity light source. One in Shanghai. They are building it at the moment. They may be ready in 3-4 years' time. And another one in Beijing, near Beijing. Okay. So again, this is although a picture, but I saw a picture. They actually start construction already. Okay. I think they proposed it ready by 2020. 2020 should be commissioned. Okay. So it's a lot of work going on this. Basically, this is a national project, okay, for extreme light, high intensity, based on this chirp pulse amplification. All these, of course, have to be based on chirp pulse amplification. As I mentioned, you could using that high femtosecond pulse to generate to accelerate charges, electron or protons, okay, to giga. Now people go to few hundred MeV now, up to giga GeV. But higher power, you go to few 10 GeV. Okay. When you go to petawatt or exawatt power, you probably able to go to tera electron volt. Okay. So with this extreme light source, a number of very exotic experiments people can do. Okay. With this stick optics experiments. Okay, as mentioned, tera electron volt acceleration, electron accelerations. You could Hawking radiation. You heard backhoe or there's not back. It actually emit radiation. You could do analogy experiments. Okay, look at this what they call Hawking UV. I don't know how to pronounce it. UV radiation. Basic analogy to Hawking radiation to learn about backhoe essentially in some way. Okay, and of course, you could pick intensity high enough. You pick the vacuum, then produce matter antimatter. So all kind of very exotic, okay, exciting experiment can be done using these high power lasers. With that, I give you a concluding remark. I don't want to go through it, but just what I said just before. But in my view, in this area, especially in my personal point of view, in the very high power laser case, best yet to come. Okay, thank you for your attention.
I am quite interested in what the y-axis is.
This one?
What is the y-axis?
Y-axis is what you call delta TOT is the experiment you need to do is all optical experiment. You're using a laser to pump it, okay, and then using a probe to probe the transmission. Okay, so the probe is I didn't talk about is what they call supercontinuum. So using an amplified pulse, you focus in a material to produce a continuum, whole visible region. And then using a laser, at this case about, I think 400 nanometer, to excite. So you create, let's say, exciton in the material. And that exciton in the material will change the absorption or transmission of the material at that point. and then you're using this to pull the change in transmission. So delta T over T is a change in transmission. Okay, so this in wavelength. Okay, it's because you pull it over a Borg wavelength. Okay, so this is a different time. You do it at different time, like K.
You mean dt is the transmission?
Yeah, change in transmission.
Okay.
With the pulse and without the pump pulse, the difference.
And I'm not sure how to measure the transmission.
Well, you're just using a detector. I mean, no, for example, silicon detector could detect photons. Okay, then no, in your camera you got light sensor. Basically, it's not a detector. You detect photon. So, but you need special one. You need very low noise, very expensive one, not those in your camera. Okay.
Okay, thank you.
What do you see would be the limit to how short the pulse can be?
How short? I mean, we already go to soft X-ray. Okay, it is this by this harmonic generation. Okay, so you go shorter, then you need go to hard X-ray or gamma ray. You need to find material able to do that, isn't it? To produce that. Okay, that's in principle, but maybe some other technique. I don't know. Okay.
So the material that you
this is gas.
Is gas.
Just gas.
Is there a particular kind of gas?
Well, yeah, the different argon they use. This a lot of the Nobel gas essentially. Okay, but different type of gas will produce harmonic in different region. Okay.
So for the optical pull, so is there a special requirement for the object which can be pulled by the opticals?
Well, I mean, for example, in this case, you need to be either semi-transparent, so you do transmission. Okay, you absorb your light, transmission, then no good. Or you could do refraction. Also, you could do luminescence. You could do time visual luminescence. So in some ways, no limit. For example, you do metal not absorb, but you could do refraction. Okay, so in principle, you can do all kind of objects.
How do we how can we assure that the electron generated at the surface is not caused by the photon?
I mean, if the charge already there, okay, then that's before the pulse. That's T. Okay, so T already take that into account. Delta T is when you know the difference between when you pump it using a pump pulse, you create, let's say, charges, and then minus the background. Okay? If you got original, got some free charges, which you may have, or you should have some, but that will be subtracted away, isn't it?
And the whole process is generated by the photon, right?
In this experiment, yeah, solar cell. I mean, hope on solar cells, using light to create charges, and then able to extract it. So here, of course, is from photon. It generates from the laser, which is photon.
And how does the electron generated at the surface moved away? I mean,
things will diffuse, isn't it? So initially by diffusion. Okay, diffusion.
If not, let's thank Professor Wang again for his comprehensive
Thank you for your attention. Thank you.